Hello everyone, my name is Jamal Nikeladi. I'm a senior researcher in the diverse team in ERISA in France. And today I'm delighted to present you our paper entitled Co-evolving Code with Evolving Metamodels. So before to start, let me just give you a background of this work, which is done on the field of model-driven engineering, where two main concepts are at the heart of MD. So instead of coding directly the software, it advised to abstract as much as possible with different artifacts, and they are separated based on their point of views. So if you have the architecture point of view, you have architecture model, etc. And in order to create those models, we use software languages. And at the heart of software language, there is what we call a meta model, which is equivalent to a grammar in a programming language. So you define here the main concepts, their properties, their relationships, etc. And then from the meta model, EMF Eclipse platform allows you to generate the language or with the core API adapters editor, and you can enrich it with additional code to perform additional functionalities like verifications, etc. So in ideal world, you want to follow this process, but of course you will develop it in an iterative manner. So you will have to evolve your meta model, and then you can generate the code, but the additional code that you have added in the previous release, for example, might be impacted and might need to be repaired and co-evolved. So let me give you an example to better understand this issue here. So this is an excerpt of the OCL Pivot meta model. There is more than 100 classes. I just took few of them. So here you have a few classes that EMF Eclipse can generate code from it. So the first step is they generate interfaces, for example, for class multiplicity element, for property. Then you generate implementation classes for them. And of course, you also generate, or EMF generates a package class, a factory class that allows you to instantiate and get the current instances of those elements. And as I mentioned before, as a developer, you will add additional code on top of this. So let's see here just two examples. The first one applies is a class Pivot validator that applies validation. And the second one applies a conversion. So it converts the element of pivot to another one. And here we can already see that the elements that we use in the code are those in the meta model. For example, here the operation validate, the class classifier type, multiplicity element, their attributes that are used some in the code, other properties, for example, on the rule here is used in the code as well. And the challenge is how, when the model evolves, how to co-evolve the code. So let me give you an example of how actually it evolved in between two versions. For example, the two classes model and multiplicity element were deleted along their properties. The operation and the class classifier type were renamed, and another property was pushed down to subclass namespace. And these changes, of course, impacted the code that I showed before. So here you have all the different impacts, and this was co-evolved by the developer by applying a rename and deleting the code that was handling the deleted class multiplicity element. And the same for the other code. So we had like many impacts, and the developer deleted the unnecessary code and replaced, for example, the owned rule that was pushed down to the subclass was replaced by another one with the same type, etc. So our approach, we propose to handle this this challenge of meta-model evolution and code co-evolution. So we propose an approach that we start from a setting where we have the code that was added on a given version of a meta-model, and then when it evolves, we get what changed in the meta-model level, and then we try to analyze the code to detect the impacted part due to this evolution, and we propose resolutions for this impacted code here. So if you see here, I mentioned 1 to n impact analysis. So basically, if as I said before, from the model you generate interfaces, class implementations, factory, etc. So, and of course, for this example of property, For example, I can use the type of the interface of the class implementation. I can use the constructor or the factory method to get an instance, and the same thing for the attributes. I can use the getter, the setter, etc. So there are n ways to use a meta model element in the code, and if this one evolves, we have to deal with n different impacts at the code level. So regarding the resolutions, what we propose, we gather the catalog of resolutions that can propagate the meta model evolutions down to the code. We did an evaluation for this work, so we took 3 languages, OCL, Modisco, and Papyrus, with 5 meta models that evolved from different versions. And we considered then project that depends on the project where the meta model is and the code is generated. And we wanted to study this coevolution of the code in those projects. So we were interested in 3 research questions. So can we first handle the coevolutions or the impact of the evolution of the meta model to the code? Can we propose the resolutions? Is the resolutions that we propose the correct ones? And then finally, if it's not the correct one, can we still propose appropriate resolutions as alternative ones? So to summarize, we had more than 900 impacts due to 477 metamodel changes across the 5 metamodels of the 5 projects. So we were able to propose the resolutions for each one of them, and almost 11 resolutions were sufficient actually to propose the resolutions, mainly to delete and rename, replace elements, but also other resolutions. And we computed a weighted average of precision and recall because some projects were smaller compared to the other ones. So we did the weighted average, and we had 87, 18.8 precision and recall for the coevolution that we were propagating. And finally, when we didn't propose appropriate resolutions, there was 9% of the cases where, for example, we could still propose an appropriate resolution. In the sense, for example, here I have an except of a code that was impacted by a change of type of the element specification and the push property of owned rule. And the code was deleted, while we could have easily co-evolved it by simply changing the type of the assignment here and adding a check of type and conversion of type to the method get owned rule. To summarize this work, we explored coevolution in software languages. We propagated meta model down to the code, and of course there is still a lot of work to do here. First, to maybe generate coevolution plans, because we still generate alternatives, but we ask the user to decide which resolution to apply. We want to extend it to GHipster, of course, and maybe apply qualitative criteria for coevolution. Thank you for listening, and yeah.